Okay, this is the first lesson in our next area of study, how do things move without contact. Alright, so it's about fields, essentially. Fields, so fields just a region around something. An object or whatever that affects other things. Alright, so it's kind of a bit wishy-washy, but the first one that we're going to look at is gravitational fields. So gravitational fields, basically, here's a bit of a diagram. So here's a diagram here, and say this is the Earth that we've got here. Then the Earth has what's called a gravitational field, and that's represented by these arrows there pointing towards the Earth. Now the reason for that is, like, if I get a ball or something and I hold it there, it's going to fall down towards the Earth. And so the thing about the Earth and the thing about the ball is that they have mass. Right, so because there's mass, there's some sort of attraction that goes on, and physicists have termed that particular attraction gravitational traction. Alright, now, this over here says the field is weaker, there's the field line spread, so the further you get from the Earth, the gravitational field strength of the Earth gets less. That's all that's on about. So there's another graph here that shows that. Right, so here's our graph. So here at the Earth's surface, we have there's a gravitational field strength. Right, we're standing on the Earth's surface, we're attracted to the Earth's surface, we don't float away. Drop a ball and the ball falls towards the Earth's surface, and according to this here, this one gives you a value of 10, but in actual fact we should be more specific in saying that it's 9.8, and it's 9.8 Newton for every kilogram. Alright, now as the graph also shows, that as we go further from the centre of the Earth, so here the Earth's surface, but really measured back from the centre of the Earth, then the gravitational field strength, as by this line, goes down. Now, it turns out that it's proportional to actually 1 on the distance squared. Alright, so that then leads us on to, and there's a video on this on the thing, so what it leads us on to is Newton's universal law of gravitation. Alright, and the video there talks about that. So it was Newton and Johann Kepler, we'll hear a bit more about Johann Kepler, that were interested in these sorts of things about planets and etc. So what Newton did is he came up with, if they've got two masses and they're separated by a certain distance r, then what Newton said is there's a force of attraction between those. And so he came up with an equation, and the equation is that the force is G, and I'll get onto that in a minute, M1, M2 on R squared. So M1 and M2 are the two masses, and R squared, R of course is the distance between. Okay, so this G, big G here, is the universal gravitational universal. It's everywhere, all over the universe that's used. And it has a value of 6.67 by 10 to the minus 11. That's some pretty funky units. Newton meters squared per kilogram squared. So those pretty funky units there. But in the end, we don't need to worry too much about those units, just using the value of it. So big G, there's our big G. Alright, so the video goes into a bit more detail than I have, of course. Alright, let's have a look at a couple of examples. So the first example, a more straightforward one. Alright, so here we've just got two people standing 1 metre apart. One has a mass of 65, the other 85. Calculate the force of attraction between them. Alright, so M1 is 65, M2 is 85, R equals 1, and the universal law of gravitation says this. So big G, of course, is 6.67 by 10 to the minus 11 times 65 times 85 over 1 squared. And then when you put that on your calculator, you get a number which is quite small. So 3.69 by 10 to the minus 7 Newton. So that's hardly very significant force, which is quite handy, because if there was too much of force between you and the person you're sitting next to, you might have gravitational attraction towards each other, which may or may not be a good thing. Alright, so that one was pretty straightforward. Now, however, you need to keep something in mind when you're doing these questions. And so here's another example which illustrates that. Alright, so determine the gravitational force that acts on a 1,200 kilogram space probe when it is 4,000 kilometres above the surface of Mars. Alright, so this is the thing I was alluding to that I didn't talk about, the thing you need to keep in mind. So if you've got something and we've got our object up here, now it's saying above the surface, so above the surface is this much there that I've done in the blue, and that's 4,000. Now, Newton's law of gravitation, or the universal law, is measured actually from the centre. So R that we need to use is that distance there. Alright, now the radius of Mars itself, so that's this bit, is 3,400 kilometres. And so what we need to do is we need to say, okay, well, the radius then is the sum of those. So the 4,000 plus the 3,400, which again is 7,400. Now that's kilometres, and of course this R needs to be in metres. So of course there's 1,000 metres into kilometres, so let's just add 3 zeros. So there we are in metres. Alright. The other thing that we need is we need another second mass. And of course that's the mass of Mars, 6.37 by 10 to the 23. And now we use Newton's universal law of gravitation and put that in our calculator. So numbers are 6.67 by 10 to the minus 11 for the gravitational constant, 1,200 times 6.37 by 10 to the 23 over 7,400,000 squared, and you stick that on your calculator and you find that the force is 913 Newton. A little bit more significant. Of course, that's because now we have some much larger masses involved. Alright, so careful when you're doing your questions. Does it say above the surface, or does it say from the centre? And because Newton's universal law of gravitation, it's from the centre. Alright, so now we know that there's a force. That brings us to what we understand as weight. So in physics, of course, weight is a force. Alright, everyday language is different, but weight is a force, and it's not just any old force. It's the force of gravity. Which is mg. Alright, so that then leads us to the concept apparent weight. Alright, so we got the real weight, and there it is, mass times gravity, and then we've got this thing called apparent weight. So when we're talking about apparent weight, it's how it appears to us. That is what we're talking about. So how do we determine like weight in itself? How do we feel it? How does it appeal to us? And it's basically it's what we feel. Oops. So what are we talking about then? Well, if we're standing on the ground, here's us standing on the ground, and we've got this weight force acting on us, bringing us down. Well, we don't actually fall through the ground holds us up. And so what we would call a normal reaction force. So when we're talking about apparent weight, what we're really talking about is this normal reaction force, and that's what we feel. We feel the normal reaction force, so it's apparent to us that we have some sort of weight. Alright, now, so it's what it appears to us. So let's have a look at an example and see, do a few calculations and see what it looks like. Now, if you've ever ridden a lift, especially some of those fast ones, if you go to Melbourne in the big towers that go up and down, you certainly feel when the lift starts and stops. And so let's have a look at an example of someone in a lift. Alright, so there you go, there's James. James is in the lift, he's got a mass of 50, his lift is accelerating upwards, and it's accelerating upwards at 2 metres per second. So let's have a look. There he is, there's James in there. Alright, so let's have a look. First of all, part A says, what is James' mass as the lift goes up? Well, James' mass, it's not going to change. Remember, mass is to do with the material. Atoms. So it makes no difference whether James is moving up, down, stationary or whatever. His mass stays the same, and that's 50 kilos. Alright, James' weight. So what's his weight? Alright, so James' weight, so weight equals mg, and he's 50 kilos times g, which is 9.8, so he's 490 Newton is James. Alright, now's where the fun stuff begins. says calculate his apparent weight. So what does he feel? So as the diagram shows, there's two forces acting on James. One is his force of gravity, which is 490 Newton, and James is standing on the floor there, and the floor's holding him up, otherwise the lift would go and he'd stay where he is. So, on James, so I'm just going to draw James as a dot. So James has two. He has the weight force of 490. He has the normal reaction force up with his feet, and the other thing that's happening is that James is accelerating at 2 metres per second. So if James is accelerating, we've then got to use Newton. So the sum of the forces is the mass times the acceleration, and I'm going to use up as positive. So what are these forces? So we've got these normal reaction force minus 490 equal James's mass, which is 50, times the acceleration of the lift, which is 2. So normal reaction is minus, we go back here, minus 490 equals 100, 0 there. Add 490 to both sides, and the normal reaction, or what James feels in his feet, is 590 newtons. So his apparent weight, so James appears or feels like his weight is greater than it was before, and so 590 newton. So yeah, if you've ever noticed at the ground floor and the lift takes off, your knees kind of buckle a little bit. There you go, that's why. Alright. So the next bit, again, I'll go back to the gravitational field. So the gravitational field, there's a definition. So what is it? So it's the gravitational force per unit mass. So what does that mean? Well, we use little g. So it's the gravitational force, which is F, per unit mass over m. Now, this force here, Newton's universal gravitational, says that the gravitational force is big G m1 m2 on r squared. Now another way that we can write that is big G big M. So big M's the big planet, little m is the thing over r squared. So if we use that and we take this bit and substitute it in there for F, we can say that the gravitational field, and so that in a few of the blank spots here, that's what we're using in there. So the first blank spot was this one, the second one is this bit, and then the third one, the gravitational field strength therefore is big G, big M, little m over r squared divided by little m, and when you do that the little m's cancel, and so the gravitational field strength depends on the universal gravitational constant, the mass of the planet or whatever it is, and the distance you are from it. Alright, so this bit here is the thing that we're interested in and going to use. Alright, so let's have a look. We've got an example here. So let's have a look at the example. Okay, so what is the gravitational field strength? 100 kilometres above the surface of the moon. So we got the mass of the moon and we got the radius of the moon. So you'll notice again it's got this above the surface. So if it's above the surface, then we need to, there it is up there, that bit there is 100 kilometres, which is 100,000 metres. This bit here is 1.74 by 10 to the 6. So the radius then is the sum of those two things. Add them up, and so that's 1.84 by 10 to the 6. Oh, I forgot my 6 over here. 10 to the 6. Whoops. There, that's a bit better. Alright, so our gravitational is big G, big M over R squared. And so big G, universal gravitational constant, 6.67 by 10 to the minus 11, times the mass of the moon in this case, so the big central body, 7.34 by 10 to the 22, over 1.84 by 10 to the 6 squared. Alright, so when you stick that in your calculator, figure it out, you get 1.45 Newton for every kilogram. Alright. So, because again you've got this R squared on the bottom, it's an inverse squared variation, like a few other things, quite a number of things in physics are. Alright, so the next thing we're going to look at is what we call weightlessness. Alright, there's a nice video there on weightlessness that you can have a look at. Now that video is kind of the closest that we can get to weightlessness, because if we take the literal, it would be having no weight. Now, seeing as weight is the force of gravity, then what we would say then is that we'd be in a place of no gravity, to be truly weightless. Now, when you have a look at what we've said is that G, the gravitational field, is big G, big M over R squared. Now, the radius thing down the bottom, so as our radius gets bigger, goes towards infinity, then what that's going to mean is that G will go towards 0. So we want to get an infinite distance from all the matter in the universe, which really is probably not going to be something that we can do. So true weightlessness is probably not something that we're going to be able to experience. But what we can do is we can say that weightlessness is sensation. So it's what we actually would feel. So that's back to that apparent weight. So do we feel like we have no weight? So if we feel like we have no weight, then we're talking about weightlessness as that. So it's a feeling. All right, so in your notes there's a few examples of things. There's 5 dot points there. So satellites are in free fall. Astronauts are in free fall as well. So the sensation of weight depends on the normal reaction force, and in that case the normal reaction force is 0. So astronauts have a sensation of weightlessness. Alright. Alright, so this is the last bit in the notes. And don't forget, notes on the website, so any of the bits you've missed in red are there. So here we are, we've got the idea. So true weightlessness, you've got to have no gravitational field. Alright, which is probably not going to happen for us. Apparent weightlessness, normal reaction force is 0. Alright, so that's probably what we're going to be able to experience is apparent weightlessness. And so in everyday language we would refer to that as weightlessness. Now, in the 2018 exam, there was a question about that concept about true and apparent weightlessness. So you need to be clear on these things. True weightlessness, no gravitational field, but we can actually have this sensation of weightlessness when the normal reaction force is 0 on us. Alright, so that's the end of the first lesson. There's a couple of videos there for you to watch in that, and then there's some questions on your text. Again, as you ever, if there's things that you're not sure of, make sure you ask me.